Welcome. In this session in linear data analysis, we'll explore what we mean by embedding a vector space. So let's suppose we have data, and these data are, we can say, some vector u, and each of them is real numbers, and there are n entries. And what we want to do is we want to embed those in a higher dimension. So we use a mapping, and in mathematics this is often written with the Greek letter phi, and it takes in a vector that has n entries, and we'll use a special notation. This is a hook arrow to indicate that an embedding is going on, and we'll map that to something. Let's say we have p dimensions, and we'll write this as, in our case, we'll always be working with observations. So let's put a bar underneath that, and then it would take in a vector-like object, which is a row. And let's go through some examples. So one example is from a previous session. We referred to that as augmentation. And in augmentation, what we can do is we'll take a vector u, or a row, an observation, and we'll embed that, and let's put a hat over it to indicate that we've done something unusual to it. So what we could do, for example, is we could take one of our two-dimensional vectors, and we can embed that in a three-dimensional space. And what worked for one sample data that we explored already is we take that observation, and then what we can do is we can add on the squared norm of that observation. And so what we would then have is we would take our 2D data, and we're going to augment or append, and it'll become three-dimensional data. And sometimes, for certain data, that will take data that are not linearly separable in 2 dimensions and convert them into data that are linearly separable in 3 dimensions. Another example is referred to as, this is a very simple example of polynomial. And a very simple example is we can take our vector that has 2 entries, which is something that we've explored previously, and we can try this. We could, in a polynomial embedding, what we can do is we can square the first entry, we can square the second entry, and then the third entry can be the product of the two. And so this is referred to as a quadratic embedding, because what we've done is we've taken a second-order function of the first, a second-order function of the second entry, and then a second-order function that combines them. And it will turn out to be useful if we multiply that by root 2. So this is an example of a polynomial embedding. Now, how can we use these? Well, let's think of it this way. What we usually want to do in linear data analysis is more or less one of 3 things. We would like to cluster, we would like to perform linear regression, we would like to perform principal components analysis. Let's think of principal components analysis. So we begin with data, and these data are all real numbers, and there are m observations and n variables. And then what we're going to do is we'll embed, and if we embed each observation, then what we end up doing is we'll take our data matrix and we'll embed that as an A hat. And now what we'll suppose is that this A hat has, we've embedded each observation, so there are still m rows to this, and now there are p columns. And then ordinary PCA is, what we would do is we would find the scatter. So let's put a little dot there, is the scatter matrix, and we would write that as S, and we'll put a hat over it, and that would then have P rows and P columns. And then we would find the eigenvectors. Vectors, which we can call, let's call them V with a hat, and these would now also have P entries to them. And we can see immediately that there are a few problems with this. One is, what do these vectors mean? How can we relate this P dimensions back to our original N dimensions? And then there is another problem, which is, if we recall from basic algebra, where we were working with polynomials, we can remember that with polynomials, the number of coefficients grows, and the term is combinatorially. In this case, in the number of variables that we have. So a second order will have 6 terms, and a third order what we'll end up with is a combinatorial explosion. And if we get a combinatorial explosion in P, then that means we're going to get a combinatorial explosion in the amount of memory that we need to represent our new data in, and we have a big problem. So what we'll do is we'll try to explore ways that we can avoid this combinatorial explosion by not doing this particular calculation. And that is going to be the subject of our next sessions.